You hear the word quantum and immediately think small, invisible, theoretical. But what if the strangest phenomena in physics were happening right now, in labs across the globe, at scales large enough to hold in your hand? What if atoms could be both alive and dead for 23 minutes? What if particles could tunnel through walls thicker than a mountain? What if information could travel without moving? These aren't dreams. These are documented effects, happening in 2024 and 2025, pushing quantum mechanics out of textbooks and into reality. 7 quantum breakthroughs, 7 effects you will see in your lifetime, each one stranger than fiction, each one real. If you value documented quantum physics and cutting-edge science like this, subscribe. It's the best way to support our work. Also comment from which city you're hearing this from. Also, this script is researched and factual. Using sources from Nature, published December 19th, 2024 on quantum error correction breakthroughs. Physical Review, letters published May 28th, 2025 on macroscopic tunneling observations. And Northwestern University's Optica Journal publication from December 20th, 2024 on quantum teleportation over active internet cables. These aren't press releases. These are peer-reviewed experimental results from CERN, Google, Quantum AI, Harvard, MIT, and national laboratories. Now back to the information. Number 1, quantum entanglement at the highest energy ever recorded, September 18th, 2024. CERN, the Large Hadron Collider. 2 protons collide at 13 tera-electron volts. Inside the compact muon solenoid detector, something impossible happens. Top quarks, the heaviest fundamental particles in existence, each weighing as much as a gold atom, become quantum entangled. Spooky action at a distance, Einstein called it. He hated the idea. But ATLAS and CMS collaborations just proved it happens at energies never observed before. Top quarks live for 0.5 yoctoseconds. That's 0.5 times 10 to the negative 24 seconds. They decay before they can even form atoms, yet their spins remain connected. Measure one quark spinning up, the other spins down, instantly, regardless of distance. The experiment analyzed proton collisions from 2015 to 2018. They selected quark pairs produced with low momentum relative to each other. This is where entanglement hits maximum strength. By measuring the angles between decay products, correcting for detector effects, both teams confirmed quantum correlations that classical physics cannot explain. University of Rochester, physicist Regina Demina led complementary work. Her team found entanglement persisting at distances farther than light can travel in the quarks. Lifetime. Published June 14th, 2024. The implications split reality. If the universe was in an entangled state after its initial expansion, what broke that connection? What made the quantum world collapse into the classical universe we observe? December 2nd, 2024. Different energy scale. Same weirdness. Physicists discover entanglement inside individual protons. A team analyzing data from the Large Hadron Collider and the Hadron Electron Ring Accelerator found quarks and gluons exist in a maximally entangled state inside protons. Distance between them, 1/4,000,000th of a meter. They share maximum information possible across that gap. The method used entropy measurements. When particles are entangled, their entropy increases, making particle sprays appear messier in collisions. By comparing spray patterns to entropy calculations, the team confirmed the quarks and gluons were not independent. They were linked. November 2024. Outer space. The International Space Station, space entanglement, and annealing quantum experiment. SEEK, a shoebox-sized device mounted outside the station. It creates entangled photons using a waveguide, then measures their states. The experiment survived launch. It works. The Bell test, designed in the 1960s by John Stuart Bell, measures if particles behave classically or quantum mechanically. CQ recorded multiple Bell violations with higher confidence than China's Mitre satellite and stronger violations than Spookhai 1, Singapore's entanglement CubeSat. Astronaut Nick Hague performed a spacewalk in January 2025 with SEEK visible in the background. The device tests whether quantum communication can work in space, where radiation constantly damages detectors. It uses laser annealing to repair silicon, i.e. heating it to fix atomic displacement from high-energy photons. May 15th, 2024. 3 cities, optical fibers, quantum internet demonstrations. 3 research groups independently achieved entanglement over several kilometers of real urban fiber networks. This is the infrastructure already buried under streets, carrying internet traffic. 1 team used existing telecommunications cables. Another created entanglement between nodes, separated by metropolitan distances. The third demonstrated quantum networking protocols that work alongside classical data transmission. These experiments, published in Nature, confirm that quantum networks don't need dedicated infrastructure. They can coexist with the internet we already have. Number 2, quantum teleportation through active internet cables. December 20th, 2024, Northwestern University, a fiber optic cable 30.2 kilometers long. The cable is carrying regular internet traffic, millions of light particles per second. Classical communications flowing through. Into this chaos, physicist Prem Kumar and doctoral student Jordan Thomas inject single photons. Quantum information. The photons survive. The information teleports. Nobody thought it was possible. Classical signals use millions of photons. Quantum information uses one. That single photon should be lost, drowned in the noise, destroyed by interference. Kumar's team studied light scattering inside fiber optic cables. They identified a wavelength that faces less interference from other signals. They chose their quantum channel carefully. Then they sent entangled photon pairs. One photon traveled with the internet traffic. Its entangled partner traveled separately. At the midpoint, they performed Bell state measurements, the quantum handshake that enables teleportation, the quantum state transferred, fidelity held. The experiment proved quantum and classical communications can share the same fiber. No specialized infrastructure needed, no dedicated quantum cables. The existing internet backbone, the cables already installed under cities and oceans, can carry quantum information. Kumar plans to extend the distance. He wants to use 2 pairs of entangled photons instead of 1, demonstrating entanglement swapping. That's when particles that never interacted become entangled. Essential for long-distance quantum networks. Next, real underground cables, not lab spools. February 2025, Oxford University. Different approach, same principle. Researchers used quantum teleportation to run a logic gate between 2 physically separate quantum processors. Not just sending information, but computing with it. 2 trapped ion processors connected by optical fiber. The quantum gate operated through entanglement and teleportation. No direct interaction. The team executed Grover's algorithm, a quantum search routine, across the distributed system. This is the difference between testing a telegraph line and sending a real message. April 2025, University of Illinois, Urbana-Champaign. They shrunk the whole setup. Quantum teleportation achieved with 94% fidelity using a nanophotonic chip, indium-gallium phosphide platform, nonlinear sum frequency generation. The device fits on a chip small enough to mass produce. One tackles infrastructure, another handles computation, the third brings everything down to size. For quantum networks, this is the roadmap. May 2nd, 2024, University of Turku, Finland, and University of Science and Technology of China, Hefei. They discovered noise can improve teleportation quality. Counterintuitive. Noise destroys quantum states. Yet by distributing entanglement beyond the qubits used in teleportation, exploiting hybrid entanglement between photon polarization and frequency up, the team achieved near-perfect teleportation despite noise. When hybrid entanglement meets noise, quantum state transfer occurs almost perfectly. The theoretical work came from Ollie Siltonen's doctoral dissertation. The experimental confirmation came from Zhaodi Liu's lab in Hefei, published in Science Advances. Number 3, Schrödinger's cat survives for 23 minutes. October 2024, University of Science and Technology of China. 10,000 ytterbium atoms, cooled to a few thousandths of a degree above absolute zero. Trapped with light, each atom controlled with precision. Each atom placed into superposition of 2 spin states. The quantum cat state formed. It lasted 1400 seconds, 23 minutes, and 20 seconds. In nature, superposition collapses in fractions of a second. Environmental noise, thermal fluctuations, any interaction destroys the delicate quantum state. But this team, led by researchers Yaoyun Yang, Wei-Ting Luo, Jianlong Zhang, Shuzhou Wang, Chongling Zhou, Tongxia, and Zhongtao Lu, used ytterbium-173, high-spin isotope, strong quantum coherence. They prepared the atoms into a cat state, superimposing opposite spin orientations. They used nonlinear spin rotation to generate the superposition. They isolated the system in a decoherence-free subspace, protecting it from light variations, the most common disruption. They applied Ramsey interferometric technique. 2 step sequence measuring phase shifts. The cat state remained stable. Sensitivity approached the Heisenberg limit, the theoretical maximum for quantum measurements. Barry Sanders from University of Calgary, not involved in the study. It's a big deal because they're making this beautiful cat state in an atomic system and it's stable. The team believes with a better vacuum system, the coherence time can extend further. This matters for quantum metrology, measurements with precision beyond standard quantum limits, magnetic field detection. At sensitivities classical sensors cannot reach. Quantum computers need qubit coherence. The longer the superposition survives, the more operations you can perform, the more complex the calculation. 1400 seconds is not theoretical. It's measured. It's the longest cat state ever observed. April 4th, 2025. Different record. University of Innsbruck, Austria, and Institute for Quantum Optics and Quantum Information. Gerhard Kirchmayr, Oriol Romero, Isart, Ian Yang, Thomas Agrenius. They created hot Schrödinger cat states. Superposition at 1.8 Kelvin. That's 60 times hotter than the ambient temperature in their superconducting microwave resonator. Conventional wisdom says temperature destroys quantum effects. Heat excites particles, increases randomness, collapses coherence. But this team used a transmon qubit inside a microwave resonator. They deliberately heated the cavity using filtered noise. Then they manipulated the system with two protocols: echoed conditional displacement and quantum coherent mapping. Both methods created superpositions of the heated states. They measured the Wagner function, a quantum fingerprint revealing distinctly quantum properties through negative values. Those negative values appeared. Quantum interference persisted at high temperature. Thomas Agrenius. Many of our colleagues were surprised when we first told them about our results, because we usually think of temperature as something that destroys quantum effects. Our measurements confirm that quantum interference can persist even at high temperature. Published in Science Advances. This opens pathways for quantum technologies that don't require expensive ultra-low temperature systems. If you can create the necessary interactions, temperature ultimately doesn't matter. Quantum devices could operate in less ideal warmer environments. Practical quantum computing inches closer. Last year, researchers placed a crystal weighing 16 micrograms in superposition, the heaviest macroscopic object ever put in quantum cat state. The field is breaking new ground into what's possible. Superposition is no longer confined to single atoms or photons. It's climbing the scale, molecules, crystals, collections of atoms. How far can it go? How large can an object be and still display quantum behavior? Nobody knows the limit. We're finding it experimentally, one record at a time. If you value documented physics and cutting-edge quantum research like this, subscribe. It's the best way to support our work. Also, comment from which city you're hearing this from. Now back to the information. Number 4. Quantum tunneling through atomic barriers. July 27th, 2025. POSTEC, South Korea and Max Planck Korea POSTEC Initiative. Professor Dong-Hyun Kim and his team solved a 100-year mystery. They watched electrons tunnel through atomic barriers. Not just slip through. They doubled back and slammed into the nucleus mid-tunnel. Quantum tunneling is bizarre. A particle encounters an energy barrier it cannot overcome classically. It shouldn't pass, but quantum mechanics allows the particle's wave function to extend through the barrier. There's a probability the particle appears on the other side. It's the principle powering semiconductors, the core components of smartphones and computers. It's essential for nuclear fusion, the process producing light and energy in the sun. But what happens during tunneling, inside the barrier, remained unclear until now. Kim's team used strong field tunneling experiments. They applied intense laser fields to atoms, forcing electrons to tunnel through atomic potential barriers. What they discovered? Electrons don't just tunnel straight through. They loop back. They collide with the atomic nucleus while inside the barrier. This collision, this unexpected dynamics, was unobserved until 2025. Published in Physical Review Letters, Volume 134, Article 2, 13201. The finding changes our understanding of electron behavior at the quantum level. It provides scientific foundation for precise control of electron behavior in advanced technologies. Semiconductors, quantum computers, ultrafast lasers, all rely on tunneling. Now we can control it better. January 2025. Different tunneling observation, communications, physics, long-range quantum tunneling via matter waves. General belief. Tunneling only occurs when barrier width is comparable to or smaller than the particle's de Broglie wavelength. This study breaks that constraint. Ultracold atoms in state-selective optical lattices. Far-separated trapping potentials. The atom tunnels to remote lattices, distances much larger than its wavelength. The mechanism? Matter waves emitted from the atom. Those waves propagate. They mediate coherent tunneling to distant sites. As long as bound states exist in the energy spectrum of the system formed by the atom and its matter wave, long-range tunneling occurs. Barrier distance becomes irrelevant. The finding, published by researchers including those at institutions studying quantum simulation, opens new avenues for tunneling devices and breaks the conventional distance constraint. 2025, Nobel Prize in Physics, John Clark, Michel Devoret, John Martinis, awarded for discovery of macroscopic quantum mechanical tunneling and energy quantization in an electric circuit. Work originated at UC Berkeley in 1984 and 1985. They demonstrated that quantum tunneling and quantized energy states manifest in systems large enough to hold in your hand, involving trillions of particles behaving as a single quantum entity. They constructed superconducting circuits with Josephson junctions, two superconducting materials separated by an ultra-thin insulating barrier, cooled below 20 millikelvin, Cooper pairs, electron pairs moving coherently as bosons, tunnel quantum mechanically through the barrier. The entire electrical circuit transitions from zero voltage to voltage-bearing state without classical energy to surmount the barrier. Observable, macroscopic, quantum tunneling. Martinis translated this directly into practical quantum computing. He led Google's quantum computing development. 2019, quantum supremacy demonstration. December 2024, Google's Willow quantum chip. Quantum error correction at unprecedented levels. Complex calculations in under 5 minutes that would require classical supercomputers 10 to the 25th years. The very mechanism of quantum tunneling now allows qubits to transition between states through quantum pathways, enabling computations impossible for classical systems. March 1st, 2023, University of Innsbruck. Roland Wester's team observed a quantum tunneling reaction. They chose hydrogen, the simplest element. Deuterium in an ion trap, cooled down, filled with hydrogen gas. 15 minutes per trial. They measured hydrogen ions formed. From the count, they deduced reaction frequency. Theoretical calculation from 2018. Tunneling occurs in 1 in every 100 billion collisions. Innsbruck measurement matches closely. First confirmation of a precise theoretical model for tunneling effect in a chemical reaction, published in Nature. It's the slowest reaction with charged particles ever observed. Tunneling reactions are difficult to predict. Quantum mechanically exact description of reactions with more than 3 particles is difficult. More than 4, nearly impossible. This experiment provides an important reference for fundamental effects in chemistry. Number 5. Quantum error correction below threshold. December 19th, 2024. Physics World. Names it Breakthrough of the Year. 2 teams, 2 very different quantum systems. Both achieved quantum error correction that makes practical quantum computing possible. Mikhail Lukin, Dolev Bluvstein, Harvard, MIT, Quera Computing. Demonstrated quantum error correction on an atomic processor with 48 logical qubits. Hartmut Nevin, Google Quantum AI, implemented quantum error correction below the surface code threshold in a superconducting chip. Errors caused by environmental noise are the Achilles heel of every quantum computer. These teams took significant steps toward overcoming this challenge. Quantum error correction works by distributing one logical qubit across several physical qubits. While each physical qubit is noisy, they work together to preserve quantum state long enough to compute. Error correction should improve as you add more physical qubits per logical qubit, but adding qubits also adds noise. The question, does making logical qubits bigger make them significantly better? 2024 answers, yes. Google's demonstration used the Willow chip, 105 physical qubits creating 1 logical qubit, but the error rate dropped exponentially as they increased surface code distance from 3 to 5 to 7. First experimental confirmation of a theoretical prediction made 30 years ago. Once below threshold, minor improvements in physical qubit quality translate to dramatic improvements in logical qubit performance. This is the turning point. Quantum computing shifts from noisy intermediate-scale quantum devices to fault-tolerant machines. August 24th, 2024. Google published results on ArcFaw. The team showed quantum error correction below the surface code threshold. That means errors decrease faster than they accumulate. Add more qubits, get better performance, not worse. Harvard's team used neutral atoms trapped in optical tweezers, 48 logical qubits, high-fidelity operations. Both teams, working independently with completely different hardware platforms, reached the same milestone. Error correction that scales, January 27th, 2025. New Quantum releases Quantum Error Correction Theory paper. Distributed quantum error correction based on hyperbolic flow codes, available on RQs. The paper demonstrates how modular quantum computing architecture of interconnected processors is compatible with high-rate efficient quantum error correction codes. Path to fault-tolerant distributed quantum computing. Google's Willow had 100 physical qubits for 1 error-corrected qubit, achieving same performance on a chip with 10,000 to 1 million physical qubits as required for transformative applications. would take many years using single processor approach. New Quantum's work shows how to build modular systems. Many small quantum processor cores, around 100 qubits each, connected via sparse network with realistic interconnect performance. Logical qubits span multiple processors, distributed error correction across the network. September 24th, 2024. Quera announces architectural fault tolerance. AFT, published in Nature. In simulations, AFT reduced time and computational effort for error correction by up to 100 times while maintaining accuracy. The approach restructures quantum algorithms, so error detection is built into computation flow. Instead of dozens of repetitions per operation, only single check per logical step. Neutral atom quantum computers, where atoms are held and controlled by laser beams, fit naturally with AFT. Any atom can interact with any other. No fixed wiring like superconducting qubits, all-to-all flexibility. Parallel operations? Hardware tests expected in next year or two. Yuval Boger, Chief Commercial Officer at Quera. Major milestone on roadmap to practical, large-scale quantum computers. February 2025. I know. Quantinuum and Microsoft achieve breakthrough. Using Microsoft's qubit virtualization system, reliable logical qubits performed 14,000 individual circuit instances with 0 errors. Unprecedented result. Multiple rounds of active syndrome extraction, essential error correction, capability for measuring and detecting errors without destroying quantum information. Quantinuum's H2 quantum computer, 32 physical qubits, created 4 logical qubits using only 30 physical qubits. Original estimate, 300 qubits needed. Microsoft's efficient encoding compressed at tenfold, 2-to-1 encoding rate. Quantinuum's market, leading 99.8% 2-qubit gate fidelity, made it possible. November 2025, Quantinuum unveils Helios, 3rd-generation quantum computer. Better than break-even performance with 50 error-detected logical qubits. Largest encoded simulation of quantum magnetism to date. 48 fully error-corrected logical qubits at 2-to-1 encoding rate. Thought impossible a few years ago. Compare. Other demonstrations would need 4,800 qubits to make 48 logical qubits. Helios did it with 96. The quantum computing industry demonstrated in 2024 that high-quality qubits can be created and successfully error-corrected. Announcements from Google, Quantinuum, Quera. Others proved we finally have building blocks to build useful quantum computers. Challenge of scaling remains, but the path is clear. Number 6, quantum sensing and atomic clocks beyond classical limits. October 9th, 2024. Caltech, Professor Manuel Endres. His team merged atomic clocks with quantum computers, published in Nature. Goal, ultimate precision allowed by nature. Atomic clocks keep time by tracking electron oscillations inside atoms. Current best clocks lose 1 second per tens of billions of years. Endres wants better. The team demonstrated universal quantum operations for tweezer clocks. Individual atoms trapped and controlled with optical tweezers, highly focused laser beams. They created entanglement between clock atoms. Entangled atoms provide measurement precision beyond standard quantum limit. Current, most precise clocks measure time with large ensembles of atoms, but individual control could lead to better performance. The team integrated quantum computing techniques with quantum sensors. They reduced errors in the system. Future work aims to push clocks closer to theoretical precision limits. Entanglement between atoms allows them to share quantum information. Measure one, gain information about all. This correlation improves measurement sensitivity. Atomic clocks based on entangled atoms could detect gravitational waves with higher sensitivity. They could probe fundamental constants of nature with unprecedented accuracy. They could test predictions of relativity and quantum mechanics at their intersection. August 30th, 2023, University of Innsbruck, Christian Roos, Institute of Quantum Optics and Quantum Information, published in Nature. The team entangled 51 ions in a chain. They used finite range interactions, where coupling decreases with distance. Spin exchange interactions allowed the system to behave collectively, all particles entangled, producing a squeezed quantum state. Using this, they halved measurement errors compared to individual particles. Previously, entanglement-enhanced sensing relied on infinite range interactions, limiting applicability. This method works with realistic finite range coupling, opening it to more quantum platforms. Quantum sensors, based on entangled particles, surpass precision of classical devices. Metrological institutions administer time using atomic clocks based on natural atomic oscillations. These clocks underpin satellite navigation, GPS, data transfer. Recent improvements use higher oscillation frequencies in optical atomic clocks. Now, entanglement enhancement pushes accuracy further. The team worked with theorist Anna Maria Ray from Gila in Boulder. They tuned ion interactions using lasers. They entangled the ions. They measured the improvement in sensing accuracy. Roughly halved error rates. July 25th, 2022, University of Birmingham, UK Quantum Technology, Hub Sensors and Timing, published in Quantum Science and Technology, Portable Quantum Clock, Ultra-High Vacuum Chamber, smaller than any yet used in quantum timekeeping. Volume, 120 liters. Weight, under 75 kilograms. Previous models come in vans or car trailers, about 1,500 liters. The team captured nearly 160,000 ultra-cold atoms in under 1 second. They transported the system over 200 kilometers. Set up time after transport, less than 90 minutes. System survived 8 degrees temperature rise above room temperature during journey. Single-trained technician can operate it. Robust, resilient, deployable outside laboratory environments. Next-generation atomic clocks are stepping toward real-world applications. Gila's Junya envisions global network of entangled space clocks. Such network could provide time standard far more accurate than GPS. Way to do geodesy and underground sensing with unrivaled accuracy. While years away, ambitious visions guide the future of timekeeping. As clocks get more precise, they enter a regime where relativity and quantum predictions collide. Einstein's relativity is incompatible with quantum mechanics. Relativity describes continuous universe. Quantum theory describes quantized universe, discrete, indivisible chunks. Atomic clocks, pushing to ultimate precision, may reveal how to reconcile these theories. They are tools for exploring deepest questions about space-time itself. Number 7. Bose-Einstein condensates at room temperature, 1924-25. Satyendra Nath Bose and Albert Einstein theorize a new state of matter. Bosons, fundamental particles with integer spin, cooled near absolute zero, occupy the lowest quantum state. The gas behaves as single quantum entity. Macroscopic quantum phenomena become visible. 1995, first experimental demonstration, rubidium atoms cooled to near absolute zero. Combination of laser cooling, magnetic trapping, evaporative cooling. Eric Cornell. Carl Wieman, Wolfgang Ketterle, Nobel Prize 2001 for achievement of Bose-Einstein condensation in dilute gases of alkali atoms. Since then, push toward higher temperatures, faster timescales, smaller sizes. Goal, make condensates practical, create extremely small light sources, enable superfast information processing. 2013, University of Michigan, Pallab Bhattacharya, near equilibrium room temperature, Bose-Einstein, condensate, not atoms, polaritons, quasi-particles, hybrid of light and matter, excitons, bound electron hole pairs coupled with photons. These polaritons are bosons. They condense at room temperature. Published in Proceedings of the National Academy of Sciences. 2013, IBM's Binning and Rohrer Nanocenter, room temperature, Bose-Einstein condensate using polymer, specially developed polymer inside microcavity, laser excitation, exciton polaritons form. They condense. Published in Nature Materials. Title, room temperature, Bose-Einstein, condensation of cavity, exciton polaritons in a polymer. Until this, only way to get BEC was freezing bosons near absolute zero. Now, organic materials with large exciton binding energies make room temperature condensation possible. Applications, energy-efficient lasers, ultra-fast optical switches, optoelectronic devices. 2018, Aalto University, Finland, Academy Professor Päivi Torma, room temperature, Bose, Einstein condensate of surface plasmon polaritons, gold nanorods arranged in periodic array, light coupled with electron plasma oscillations. The condensate forms in 1 picosecond, 1/1,000,000th of a second, fastest condensate, fabrication easy, standard nanofabrication methods, electron beam lithography. Array geometry easily varied to modify condensate properties. The challenge, proving something exists that only lasts 1 picosecond. Solution, initiate condensation with a kick so particles start moving. As condensate forms, it emits light throughout the nanorod array. Observe the light, monitor how condensation proceeds in time, turn distance into time, 2021, organic single crystal microribbon, natural cavities, room temperature, exciton, polariton, Bose, Einstein condensation. Regularly shaped microribbons serve as waveguide, Fabry-Perot microcavities. Strong coupling between Frenkel excitons and photons generates polaritons. They condense at room temperature. Published in Nature Communications. The advantage, No external high-finesse microcavity needed. Microribbons themselves act as cavities. Better compactness. Integrability on chips. Practical applications in on-chip integration. 2024. Multiple breakthroughs. ACS Photonics publishes room temperature Bose-Einstein condensation of polaritons in GAACE algas structure. Hassan Al-Natta, David Snoke, Princeton. University of Pittsburgh. Canonical properties of BEC and weak coupling regime, previously seen only at low temperatures, now at room temperature. Nonlinear energy shift showing polaritons are not non-interacting photons. Dramatic line narrowing due to coherence. Coherent emission with spectral width, 0.24 millielectron volts at room temperature. No external stabilization. Opens possibility of room temperature, nonlinear optical devices based on polariton condensation, 2024. Nature Photonics. Bose, Einstein, condensation of photons in vertical cavity, surface emitting laser, another platform. Another demonstration. Room temperature, quantum phenomena spreading across material systems. The easier creating these condensates gets, the more routes open for technological applications. Both lacing and Bose-Einstein condensation provide bright beams, but coherence properties differ. Different applications require different coherence. BEC light can have different fluctuations and correlations than laser light. The new condensates produce extremely short light pulses, faster speeds for information processing, imaging applications, quantum computing applications, where maintaining quantum states at practical temperatures is critical. 7 quantum effects, 7 breakthroughs happening now, entanglement at record energies inside the heaviest particles, proven at CERN with top quarks colliding at 13 tera electron volts. Published September 18th, 2024. Teleportation through active internet cables, Northwestern University, demonstrating quantum information surviving alongside classical traffic over 30 kilometers. December 20th, 2024, Optica Journal, Schrodinger's cat lasting 1400 seconds, University of Science and Technology of China, 10,000 Wetterbium atoms in superposition, October 2024. Quantum tunneling mystery solved after 100 years, post-tests and Max Planck watching electrons loop back and collide with nuclei mid-tunnel, July 27th, 2025. Physical review letters. Error correction below threshold. Google Quantum AI and Harvard MIT Quira demonstrating practical quantum computing is finally possible. December 19th, 2024. Physics World Breakthrough of the Year. Quantum sensing with entangled atomic clocks, pushing measurement precision to ultimate limits. Caltech merging quantum computers with atomic clocks. October 9th, 2024. Nature. Bose-Einstein condensates at room temperature across multiple platforms, from organic polymers to gold nanorods to semiconductor microcavities, proven from 2013 through 2024 in Nature Materials, Nature Communications. ACS Photonics. These aren't predictions, these aren't thought experiments, these are observations, measurements, peer-reviewed experimental results with exact dates, institutions, researcher names, publication venues, specific numbers. 1400 second coherence time, 13 teraelectron volts collision energy, 30.2 kilometer fiber optic cable, 48 logical qubits, 94% teleportation fidelity, 1 picosecond condensation time, 0.24 millielectron volt spectral width, 105 physical qubits, 51 entangled ions, 1 quadrillionth of a meter separation. These numbers are real. They're in the papers. They're repeatable. 2025 is the International Year of Quantum Science and Technology, declared by United Nations. June 7th, 2024. 100 years since initial development of quantum mechanics. Breakthroughs are accelerating. Google added over $100 billion to market cap within hours of announcing Willow Chip. Investors and organizations recognize unprecedented compute power quantum computers will enable. Companies think about how quantum computing might disrupt their business, actions to take now to prepare, how to leverage this tool for competitive edge. There's no doubt powerful quantum computers are not if, but when. Quantum effects are climbing from microscopic to macroscopic, from single particles to trillions of particles behaving as one, from absolute zero to room temperature, from laboratory vacuum chambers to active internet cables, from theoretical limits to engineering challenges. The quantum revolution is not coming, it's here. You will see these effects shape technology within your lifetime. Quantum networks for unhackable communication. Quantum computers, solving problems classical machines cannot touch. Quantum sensors, detecting gravitational waves, mapping underground structures, measuring time with precision that redefines navigation. Quantum materials exhibiting superfluidity, Zero resistance, collective quantum behavior at practical temperatures. Late reveal, October 24th, 2025. Nature publishes study showing classical gravity can generate entanglement when combined with quantum field theory for matter. Researchers Joseph Aziz and team demonstrate that both classical and quantum gravity produce entanglement via different mechanisms. Observing entanglement alone does not unambiguously indicate quantum gravity. Experimental parameters and entanglement strength remain crucial. This complicates decades of work, trying to prove gravity is quantum by measuring graviton-induced entanglement. Feynman's proposed experiment from 1957 is still useful, but the interpretation changes. Classical gravity with quantum matter can mimic some signatures previously thought to prove quantum gravity. The fabric of reality may be composed of fundamentally interconnected, non-local pieces defying everyday experience. Entanglement is property of space and time itself. Separate measurements correlate to higher degree than classical explanations allow. Einstein derided it, Bell tested it. Aspect, Ast, Clauser, Zeilinger won Nobel Prize 2022 for experiments proving it. Now we're pushing it to top quarks, protons, satellites, distributed networks. Teleportation protocols enable quantum communication without direct transmission. Superposition survives 23 minutes in trapped atoms. Tunneling allows particles to pass through barriers they classically cannot overcome, happening in your smartphone, in the sun, in superconducting circuits, producing macroscopic quantum effects. Error correction crosses threshold where adding qubits improves performance. Quantum sensors entangle particles to measure beyond classical limits. Bose-Einstein condensates form at room temperature in multiple material systems. Quantum mechanics is no longer just theory. It's engineered, controlled, deployed. 7 effects you will see in your lifetime. Each one documented, each one real. Cold numbers proving warm science fiction becoming hard engineering fact.